Hello dear friends. Today we are going to talk about the applications of integral, which is the third chapter in our book. We know from the first and second chapters that if we know the rate of change of a given quantity, then we can find the total of this quantity by the application of indefinite or definite integrals. Then in this chapter we are going to discuss finding the total functions of given quantities. For example, if P represents the total profit, this P may be found from the marginal profit, which is defined as the derivative of the profit function. Likewise, if we know the marginal revenue, dr over dx, then we can find the total revenue. And similarly, we can represent the total cost of a function, total cost of a quantity, by using its marginal cost. So, if we integrate the marginal profit, or if we integrate the marginal revenue or the marginal cost, then we obtain these total functions. One of the fundamental laws in economics is the supply and demand law. If you remember, the demand is the quantity of a of a commodity or a service that service that people are willing to or able to buy at a certain price. Similarly, the supply is the amount of a product per unit of time that producers are willing to sell at various given prices. If we denote the demand by D and if we denote the demand by S, these functions have such graphs, and they may be denoted like this. In this graph, Q is the quantity and P is the price of this commodity. Now, what's total utility? If we are given a demand function, the total utility is the area under the graph of the demand function for a given quantity Q star. So the area under the graph is the demand function when Q star units of a certain quantity is demanded, and it's calculated, this area. We already know that this area corresponds to the definite integral of the demand function from 0 to Q star. Now we are going to talk about the consumer surplus. If consumers may buy a product under a price that they are willing to pay, this may be considered as a gain for the consumers. So this extra amount that the consumers are going to pay, which is actually going to be less than they are going to pay, is the gain of the consumers, and it's denoted by this yellow area. So the actual consumer expenditure is P naught times Q naught, and the total amount spent at maximum price, assuming that the maximum price is Q naught, is denoted by this integral, so the area under the demand curve from 0 to Q naught. So the consumer surplus is this yellow shaded area, which is the difference of this total area under the graph of the demand function minus the actual consumer expenditure. So this little amount, it may be a big amount or maybe just a little amount, is called the consumer surplus. Just like the consumer surplus, we can define the producer surplus. If a producer who's willing to sell a product may sell his or her product at a higher price, then this difference between the prices and the money this producer is going to get is called the producer surplus. So if S is the supply curve and P naught and Q naught are the price and quantity respectively, the producer surplus is defined as the integral. Well, it's not actually the integral, I'm sorry. It's the area under the graph of the supply function subtracted from this rectangle P naught times Q naught, and this small shaded green area is going to correspond to the producer surplus. So the equilibrium point, as you remember, is the point where the supply and demand are equal. So given the supply curve S and the supply curve, demand curve D, the intersection point is called the equilibrium point, and at this point we can also calculate the consumer and producer surpluses. And if you just plot the supply and demand curves, calculate the equilibrium point, so this yellow shaded area will correspond to the consumer surplus, whereas this green shaded area will correspond to the producer surplus. Now, in order to measure the distribution of income, various methods have been employed. One of the most commonly used one is the Lorentz curve, which was developed by Max Lorentz in 1906. The Lorentz curve in this graph represented by this greenish curve is constructed in this way. First, people in society or the households are sorted from the lowest income to the highest income. Then, by the total portion received from the total income of a country is divided into these households. At every population, well, at every household, the total income is calculated, and so on and so forth. You go up to 1 and you calculate all the incomes divided to all the households, and you get this Lorentz curve. Now, Lorentz curve is a curve between 0 and 1, and the Lorentz curve is an increasing function. If Lorentz curve, well, or let's say Lorentz function at 0 equals 0, which means that if there is no, how should I put, if there's no income, there is no, there is no income if there's no job, something like that. So at, let's say x equals 1 or p equals 1, Lorentz curve becomes 1. So if everybody is working, the total income is 1. So the Lorentz curve L of x is always less than the line y equals x. Now, line y equals x will correspond to perfect equality, perfect distribution of income, equally distributed to the population of a country. Now, there's another very important concept which is called the Gini index. It's a measure of the income inequality. It is, if we go back and have a look at our figure, it is twice the area. It's twice the area between the perfect equality line and the Lorentz curve, which is the inequality gap. So the Gini index is calculated as the area, as twice the area of this region, which is given in terms of this definite integral, x minus L of x, integrated from 0 to 1. So the Gini index is does change from 0 to 1. Now, what it means that Gini index is 0? It means that everybody has the same income. So everybody is sharing the total income of a country equally. If Gini index is 1, it means that the total income of a country is received by a single person or by a single company, so to speak. Yeah. Another subject we may use integral to calculate is the present and future value of an income. So the present value is a financial calculation that measures the worth of a future amount of money or stream of payments in today's liras, adjusted for interest and inflation. So if f of t is the income function, r of t is the annual rate of inflation, and e to the minus rt is a damping factor, then the actual income is the integral of f of t in the time period from 0 to capital T, and the present value of money is f of t times e to the minus r of t integrated from this from 0 to t, which is the time interval we are trying to find the present value of our money. Likewise, we may talk about the future value of money. Now, just as before, if f of t is the income function, then r is sorry, not then, of course, but r is the annual rate of inflation and e to the minus rt is the damping factor, then we have the future value as the future value of the money, the integral of f of t times e to the r times t minus t. But we need to just be careful about the present and future values of money, such that in this case, the integrand, the exponential function in the integrand has a positive exponent. So r times t minus t is positive, whereas in the present value of income, it was e to the minus rt, and it was a negative exponent, which was signifying a decaying function. But in this case, we have an sort of increasing function, okay? Well, not exactly an increasing function, but still a positive function multiplying the f of t. As I have said at the very beginning, the integral may be used to calculate the total functions of quantities which are given in terms of their rate of changes. So I suggest that all these subjects are quite detailed in the book, in your book in this chapter, and you can go and solve as many questions as you like. And also you may consult your economics books, because these concepts are frequently used in your economics books. So thank you for listening. See you next time. Bye bye.